Good evening, ladies and gentlemen. I'm Kino, STEMwithKino.com, and today we are going to be covering aviation and nautical information. This will be oral. You can't see my client, but we are going to cover some things that you should be aware of if you are preparing for the aviation selection test battery, and in particular, the aviation and nautical information. So we're going to cover some stuff in a minute. I'm calling my client now, and we will jump in a minute. Hello.
Hello.
How you doing? Okay.
I'm a little tired, but otherwise okay.
That's all right. We're going to get through this, my brother. Okay, so aviation and nautical information, and congratulations on your score during the first part of the OAR portion. All right, so
Thank you.
congratulations on that, and we are preparing for the aviation and nautical information portion of the test.
Yeah.
And give me a moment. I'm scrolling. All right. Almost there. Hey, buddy. Okay, I can jump ahead. What are the four forces of flight?
That is thrust, drag, weight, and lift, or gravity.
Okay, are you aware that there are subcomponents of one of those forces of flight?
Yes.
Okay. Which force and what are the subcomponents, if you can remember them?
The force is drag.
Very good. That is correct.
And the subcomponents are induced drag and parasite drag.
Very good. Now, let's talk about how these subcomponents are created. They make up total drag. How is induced drag created? And if you don't know, just say I don't know, and we'll talk about it.
I'm not sure.
Okay, very good. Okay, can you see my little replica, my little miniature airplane here? Okay, not that plane. Let's do this one. All right, so we have our miniature airplane here. Now, there are airflow patterns that exist when this aircraft is flying through the air. Okay. On the upper side of the wing, or on the upper camber or upper curvature of the wing, the airflow is going to actually flow towards the fuselage.
Okay.
The lower pressure area. In the higher pressure area, it's actually going to flow away from the fuselage. Now, if we had what's called an infinite wing, where this wing would go forever and ever and ever and ever and ever, which is not the case. The low pressure and the high pressure airflow, if you would, they would never meet each other unless they were at the back. But they wind up meeting each other because we have a finite wing. They meet each other on the edges, and they produce a disruption, like little small hurricanes. And we could either call it a vortex singular or vortices plural. All right.
Yeah.
So So just because we're using lift, we're going to get parasite drag. We can't get away from it. I'm sorry, induced drag. Sorry. All right. Parasite drag just comes from just having parts join each other, which we're going to get into in a second. What are the five major components of aircraft? There are five major components every airplane must have in order for us to call it an airplane. Whether we're talking about this guy or we're talking about this guy. All right. There are five major components. Can you name them?
So we have the fuselage.
Very good. And what is what does the fuselage do?
It's the body of the aircraft.
Okay. It houses the cockpit, air crew, passengers, and cargo, depending on its mission and the purpose of the aircraft. Okay. This one has a very large fuselage and it can hold a lot of passengers and cargo. As opposed to the mission of this airplane, which you only have one pilot. Okay, so there's no passengers, there's no cargo, or I guess if you wanted to consider the payload cargo, you could. All right, but there's and it's important to remember this is a rotary wing aircraft. It does have a fuselage and everything like that, but it's different. It's different because it doesn't have wings, which is another major component of an airplane. All right, so this does not have wings. All right. Now, we talked about the fuselage. We talked about what it does. We talked about wings. What is the purpose of the wings?
The wings are what helps generate lift.
Very good. Or I like to say the wings support the weight of the aircraft in the air.
Okay.
If that does that, then the landing gear do what?
The wing, that would support the weight on the ground.
Yeah, so when we're parked, when we're taxiing, taking off, landing, then the landing gear does its job. All right. So we talked about the fuselage, we talked about the wings, we talked about the landing gear. We have two other components. If you can remember them, let me know what you think they are, if you can remember them.
The other one was the empennage or the tail section.
Or the tail section. Okay. The empennage, it's a French word, but it means tail section, and it consists of a vertical and a horizontal stabilizer. You can see kind of like that inverted T formation. Sometimes you'll have a slant in your vertical stabilizer. The horizontal stabilizer is still horizontal in this case, and I'm putting it up to the camera. All right, so you could have like a T, or you could have like a little slant. It depends on the design of the aircraft. Okay, very good empennage. And then finally, the last major component.
The power supply.
The power plants. Why don't we just call them engines?
Because some of them function differently than just a standard engine.
Okay, I don't like that answer.
Okay.
And it's okay. It's okay. This is where you make your mistakes, not on the test. We call them power plants because they do more than just drive the aircraft. Engines provide pressurization in some aircraft, electrical energy, pneumatic energy, vacuum power for the instruments. In some cases, I don't have like a little single engine airplane replica, but in some cases, the engine actually drives the alternator, and the alternator sends the electrical energy back to the battery that you used. Because every time you turn that key, you're lowering your battery, you're taking some juice away from the battery. And so as a result, you need that alternator to send that juice back to the battery so you can restart again. Okay, so the five major components of an aircraft are the fuselage, wings, landing gear, and fuselage. All right, let me back up. Fuselage, wings, landing gear, empennage, and power plants. Very good. I'd like you to tell me if you can remember. There are three axes of rotation. Singular would be axis, but when we say plural, we say axes. Do you know them?
I'm sorry?
Do you know the 3 axes of rotation that the airplane moves about?
So you have your vertical axis.
Okay, pause there. What is the movement about the vertical axis called? And I want to know the flight control surface used to do it.
That's called the yaw.
Yaw. And what is the flight control surface that's used to do that?
That's the rudder, which you control with the foot pedals.
Very good, very good. Okay. Name another axis of rotation.
You have your longitudinal axis.
Your longitudinal axis. What is the movement and what are the control surfaces that make that happen?
Your longitudinal axis is your bank axis.
Okay, we roll around the longitudinal axis. So the longitudinal axis, if we're rolling about the longitudinal axis, then the plane is doing a little motion like this. Okay. As opposed to, we talked about the vertical, we yaw about the vertical axis. We roll around the longitudinal axis. All right. What is another axis or axis of rotation?
Your lateral axis.
Very good. Your lateral axis. Okay. What is the movement called about the lateral axis? What is the movement we perform? And what is the flight control surface responsible for making that happen?
That is your pitch.
Your pitch.
So nose up, nose down.
Very good. Very good. So we pitch nose up, nose down about the vertical axis, kind of like a roller coaster. Yaw, I liken yaw to like your car. Your car yaws when you make right and left turns. Your car is making a yawing motion. All right. Very good. Very good, very good, very good. I can tell you've been reading. That's always a plus. All right. Okay, so we talked about the 5 major components of an aircraft. We talked about the axes of rotation. All right. We talked about our flight control surfaces. We have ailerons, we have rudder, and we have elevators. Now, flaps. What are the purpose of wing flaps?
The flaps are used for, they can be used to slow your airspeed.
Okay, drag does occur, so in landing we do get slower. We also delay our stall speed. For instance, let's say, and I'm exaggerating this a little bit, but just to give you an idea. Let's say we were doing a landing with no flaps. Number one, let's say our stall speed was 100 knots. And we extended our flaps, and our flaps let us get down to 75 miles per, or 75 knots. Would you rather land at 100 knots, or would you rather land at 75?
75.
You want to be slow as possible, okay? Because that just kind of, until you kind of get more experience with faster aircraft, and then then maybe you can handle those high speeds. But especially in training, you want to be nice and slow and stable as possible. And flaps give us the ability to do that. With the greater amount of curvature that we get in the wing because of flaps, we get more lift, but we also get more drag as well. So that prevents us from kind of getting too speedy or fast because that drag is going on. All right. Landing gear. There are 2 types of landing gear configurations. Do you know what they are?
I know one is the tricyclical landing gear.
Tricycle. Just tricycle, like little, you see the little kids out on the playground, they have their tricycles and stuff like that. That is because you have a steerable nose wheel. This is a replica of a tricycle gear system. We have a steerable nose wheel, and then we have have two main landing gear. But these don't steer at all. This is the nose wheel that it pivots left and right and allows us to taxi. All right. Same here. I don't have a tail dragger replica, but same here. We have the nose wheel here, and we have the two main landing gear here. So that is the tricycle type landing gear system or configuration. What is another configuration an aircraft could be in?
Well, I'm going to give it the informal name, but there's the tail dragger.
Very good, the tail dragger, and we call that the conventional. It's a conventional landing gear. All right, the tail dragger. Two main gear up front, and you have a steerable tail wheel. And the reason why they call it a tail dragger is because a lot of times when you see these aircraft, they're kind of tilted, like their nose is pivoted up towards the air because their tail does the steering, and hence tail dragger. Okay. Could you define Bernoulli's principle for me? If you can't, don't worry about it. This is all we're prepping. We're test prepping. But if you don't know it, it's something I would write down because it's probably something that could possibly pop up on the test. And it's something you need to research anyway. So
Bernoulli's principle, I know we went over mechanical. I don't think I'll be able to give the exact definition, but
Daniel Bernoulli was a Swiss physicist that came up with the principle. And the principle states that as the velocity of a fluid increases, its internal pressure decreases. As the velocity of a fluid increases, its internal pressure decreases. Now, as far as I know, Daniel Bernoulli had nothing to do with airplanes at all. He actually studied the movement of water and liquids. And liquids and air act very similar. But he used something called a Venturi tube with a constriction in the middle. And so that's why I'm drawing this little tube with the constriction in the middle. And he noticed something. Like if we had a velocity, something to measure how fast, and the pressure of something at this point, and this point, if we had gauges, and we pushed water through there, or we pushed air through this Venturi tube, then what would happen is we would note an increase in speed and a decrease in pressure. All right. And so that's hence, as the velocity of a fluid increases at this point, its internal pressure decreases. And this thing is called a Venturi tube. A Venturi tube is a tube with a constriction in the middle.
Okay.
Now, another thing, too, is sometimes jet propulsion systems are kind of designed in this way, where you may have, like, the outside cowling of the jet engine, but inside they will put, like, a little constriction in there, and then you'll have, like, your turbine, your intake and compressor, your turbine, fans, and everything in there. But you still get this increase of pressure in the inside the cowling of the turbine and stuff like that. So it just makes it just more efficient and increases the airflow and things of that nature. So back to Bernoulli's principle, though. So if we looked at the bottom of this Venturi tube, we could actually fit something in here called an airfoil. What is an airfoil?
An airfoil is something that can move through the air to generate lift.
Okay, I like that. Let me give you a shorter one. Airfoil is any device that's used to produce lift.
Okay.
The main rotor on this helicopter replica would be considered an airfoil. The tail rotor would be called an airfoil. They just produce lift in a different way. Vertical lift is produced by the helicopter. Lift is produced by the airflow over the top and the bottom of the wing, and we get negative pressure on the top because as the velocity of a fluid increases, its pressure decreases, and then we get positive pressure on the bottom. Newton's third law of motion in physics. So you want to definitely know Bernoulli's principle. It's not going anywhere. You'll definitely hear about it in API and need to know it when you go to API. And definitely primary, and the airfoil, any device used to produce lift. All right. Okay. All right, let's move along here. And you're doing a great job. But these are some basic principles that we need to just be aware of. Now, can you remember the 6 basic flight instruments?
You have your attitude indicator. So you have your airspeed indicator.
Very good. Your airspeed indicator.
Your attitude indicator.
Your attitude indicator.
You have your vertical speed indicator.
Okay, that's down here. All right.
You have your altimeter.
Your altimeter's up there. Very good.
You have your heading indicator.
Heading indicator, bottom center.
Your turn coordinator.
Very good, your turn coordinator. All right, so from left to right and top and bottom, airspeed indicator, attitude indicator, altimeter, turn coordinator, heading indicator, and vertical speed indicator. Now, in some more advanced aircraft, you will not have these dials here. You might have a head-up display. You may have an EFIS, which is a electronic flight instrument information system. And I think I've showed you on the simulator a couple of ways that they could be displayed. But you will get a lot of the same information like airspeed, attitude, altitude, heading, and possibly vertical speed indications. So what they've done is they've just consolidated something and just put it on a heads-up display glass. So you can keep your eyes outside of the aircraft and see what's going on instead of staring or peering down into an instrument panel. All right, very good. The basic 6 flight instruments, okay? And make sure you understand how they work, the color coding, and the color coding inside the airspeed indicator. All right. Good. All right. Can you define for me ground effect? If I asked you, what is ground effect?
I just looked at that today, too.
It's all good. If you don't remember, just say, I looked at it, but I don't remember it. It's fine. You're in the early stages here, so it's allowed right now.
Ground effect. I'm not quite sure.
Okay, very good. Okay, so let's say this airfoil, our airfoil, we're at 2,000 feet. And our airfoil is just flying and we're getting the laminar airflow we want. But we have to understand there's a natural upwash and downwash because we have all this air below the wing. So nothing is really disturbing the airflow around the wing. Okay, so we have our normal upwash and downwash. Now, this is great, but when we get within one wingspan, typically around runways, when we get within one wingspan of the Earth is going to interfere with this normal upwash and downwash pattern. So we're going to have our lift, we're going to have our thrust, we're going to have our weight of the aircraft, but our drag is going to be minimized because of this disturbance. So we're going to have the same amount of lift and thrust, and we're going to have reduced drag when we're within one wingspan of the Earth. All right. So up here at 2,000 feet up high, we don't have any issues. When we kind of get within one wingspan of the runway, we can get some potential disturbances, aerodynamically speaking. So on hot and humid days, you'll find that this is very, very pronounced. There's some days where you want to come in for a landing and the plane feels like it just does not want to land, especially if you come in too fast. Because you're generally, if you're coming in really, really fast, you're generating lots of lift. And the plane's going to be like, no, I want to fly. You're like, no, I want you to land. No, I want to fly. I'm sorry, I want to fly. So,
yeah,
you know, your instructor pilot will show you a technique. You know, number one, on very hot, humid days, you can expect some ground effect to go on. And it will probably be a little bit more pronounced than, you know, any other day than a hot, humid day. But the thing is you don't want to float halfway down the runway trying to put it down, and then you actually get slow enough and you land, and then you only have a couple hundred feet of runway. A lot of people have run off runways because they were just, I got to get it down. So the goal typically, in a lot of cases, is to be down on your first third of runway, about the first third.
Yeah.
Or in the threshold, the landing threshold area. Okay. We'll discuss that. Propulsion systems. Can you name two types of propulsion systems?
So,
and we're talking about our power plants.
Yeah. So you'd have your turbine engine.
Yep. Turbine.
And you'd have the combustion engine.
Well,
or
I'd stick with turbine or propeller or turboprop or turbo propeller.
Yeah. I was I was gonna say prop.
It's all good. So with our propeller airplanes, most propeller airplanes are piston driven. Don't laugh at my artwork.
Nope.
So we have a crankshaft that's connected to an engine, and then we have cylinders. You have a 4, a 6, an 8-cylinder aircraft, and it's very similar to your car because your car has cylinders. And there's some things that go on with the internal mechanisms. Normally, it's what we call a 4-stroke engine. 4-stroke. Okay. And there's power, or no, there's intake. And even if it's a jet engine, it's going to go through same phases. It's going to be an intake phase, a compression phase, a power, or what we would call combustion, and an exhaust. So even with the propeller and the reciprocating engine, this 4-stroke engine has these 4 cycles of 4. Yeah, I guess you just call them cycles. There'll be an intake stroke where they draw in air, a compression stroke where they compress the air, and they atomize. Do you know what atomization is, or atomizing something?
Nope.
Okay. Do you wear cologne?
No, I have no.
What about, I don't know, some type of spray-on hair gel?
And what about spray suntan lotion?
Okay, spray suntan lotion works. Well, if the bottle was clear and you shake the bottle, there'd be fluid in there, wouldn't it?
Yeah.
But when you spray it on your body, it's a mist. It comes out in the mist. It's atomized. It's not in this liquid form. So something goes on very similar with the fuel injectors inside the cylinders during that compression phase. It's squeezing the air and it's spraying fuel in there, right? Then all of a sudden spark plugs light off, and then boom, that's combustion. And then after that, the fuel air charge is ejected out and away. All right. But if we look at our turbine engine, you have your intake blades that suck in the air. Then you have your tighter arranged compressor blades squeezing the air. And in the combustion chamber, you'll have your fuel injectors spraying fuel into this situation, causing the combustion. And the cool thing about this is you get air expansion. When it heats up, it expands. And then it's just blown out the back for jet engines. It's just blown out the back. But there's been a physical change to that air. Okay, because the air molecules were spaced far apart. But then when it got to compression section, the air molecules are squeezed tightly together. And we atomize, put some fuel in there, and then boom, and then it expands. And this is the reason why jet engines are they're high performance. They can produce many pounds of thrust, more so than a propeller. Now, sometimes instead of pistons driving the propeller, you could have turbines driving the propeller. Right? So this jet engine is spinning, but it's connected to a crankshaft of some sort. Or maybe it's offset with some gears and then connected to a propeller. And we call that a turbo propeller or a turboprop for short. You know, pilots always have nicknames for stuff. It's a turboprop. All right. The Pitot static system. Any idea what that is, the Pitot static system?
That is what helps measure your airspeed indicator.
Okay, it's part of it. You have three engines. You have three instruments: airspeed indicator, altimeter, and VSI, your vertical speed indicator. Now, normally on the body of the aircraft, you'll have a Pitot tube, and the Pitot tube just kind of hangs down like this and points forward. All right, and as the aircraft flies through. And then, sometimes there's a drain hole. Like if you run into rain and stuff like that. Then the water simply just goes in and then it's ejected out the back. No worries. No issues. And it has very little, like a change in accuracy. There's very little change in accuracy when it happens. So they want it hanging out so it can get into the real slipstream or relative wind. And then this feeds into a line that goes to your airspeed indicator. Now, when you pre-flight, your instructor probably told you, don't touch the static port. The static port is normally flush with the skin of the aircraft, and you see like a little pinhole in it. And you don't want to touch that with your hand because it's a very fine hole. And you may have oils in your hands, contaminants and stuff like that. So you just don't want to be rubbing around the static port. Now the static port feeds all three of these. The ram air or the Pitot tube only feeds the airspeed indicator. That's it. All right. Ram air only goes to the airspeed indicator casing. The static port is connected to all three. Now we'll go in depth with how an airspeed indicator works down the road a little bit here. But that is the Pitot static system. It consists of your Pitot tube, your static port, which gives you static pressure. Whatever altitude you're flying at, there's a given pressure. And it feeds your instruments. So it tells your instruments when you climb and descend. When you climb, you reduce pressure, atmospheric pressure, right? When we descend, we lower. We increase. So climb, decrease in atmospheric pressure. Descend, increase in atmospheric pressure. So all three of these instruments, and definitely your altimeter and your VSI, they sense these pressure changes as you increase in altitude or decrease in altitude. The VSI is, that thing will jump. If I pull back on the nose, the VSI just boop, it'll pop up and say, hey, you're flying at 1,500 feet per minute or whatever. Your altimeter is a little bit slower. It's a little bit slower. Now we'll go more in depth with these other instruments because sometimes you may not just have an VSI, but you may have an IVSI. An IVSI is an instantaneous vertical speed indicator. All right. So this is not instantaneous, a regular VSI, because it has a calibrated leak. It kind of needs you to get into a tendency of climbing, level, or descending in order to really give you a proper reading. It'll kind of fly around a little bit and bounce around until you stabilize your flight condition. But the IVSI is like, bang, it's right there. It's telling you immediately, hey, you're climbing at 500 feet per minute or 1,500 or 2,000 feet per minute, whatever the performance of your aircraft will allow. That IVSI is like all over it. All over it. Okay. Your attitude indicator, ouch. Your attitude indicator looks kind of something like this. And you'll have your artificial horizon. And you'll have your miniature airplane in there. And you may have some pitch markings. 10 degrees, nose up, 5 degrees, nose up, whatever, what have you.
Yeah.
This is one of your gyroscopic instruments. You ever play with a spinning top when you were a kid? No?
Yeah, I did.
Okay. So we take that top and we spin it. And it spins really, really fast. And what does it do? It just kind of stands on its tip, doesn't it? It spins and everything. This is called rigidity in space. All right, and I want to just, because there's there's a gyro inside of here with a weighted rim, and actually we use a vacuum to suck air through this case past something called the pendulous vanes, and they actually cut that airflow, and it keeps spinning.
Okay.
So as long as you have vacuum pressure or suction, this thing should be nice and stable. If you're level flight and this thing just starts to, sometimes you'll have a flag that will say, that'll pop out here and say off to let you know that it is inoperative. Or meaning that we're not getting enough vacuum pressure. Sometimes you could be at an idle flight condition where you pull your engines all the way back. You'll get less suction and this will degrade, but that's typically on the ground. When you're in flight, when it's needed and you jam the power, you're at full power or cruise power setting, then enough air is flowing past this and it will stabilize really, really nice.
Okay.
All right. Now, sometimes for aerobatic maneuvers, we may need to cage the gyro or lock it up so it doesn't go out of parameters. All right. So that's gyro caging. Like you'll note that in say like the T6 when they're doing aerobatic maneuvers and stuff like that. 9 times out of 10, they're probably gonna cage the gyro. So this way the aviation mechanics don't have to go in there and toy with it and stuff. They'll just cage it, and when you get back to level flight, they'll uncage it, and then it'll be free to spin again.
Okay.
Alrighty. All right, there are a couple more gyroscopic, if I can pronounce the word, gyroscopically driven instruments. These would consist of your heading indicator and your turn coordinator. All right. If, for instance, your vacuum system failed, you can use your turn coordinator to maintain level flight. All right. But it's powered by a gyro, so there's some redundancy there. Nothing is driven by, most things are not driven by the same system. They're driven by different systems because if this system fails, we can still maintain level flight using this. This doesn't use vacuum pressure. It's an electrically driven gyro. And what you may see on the turn coordinator, you'll see DC elect, meaning direct current electricity drives me. That's what the instrument is telling you. Hey, you don't have to worry about the vacuum system. I'm driven by direct current electricity. And so I'm not relying on high cruise power settings or anything. It'll just kind of do its thing. And we'll go more in depth about that as well. Have you ever heard of wing dihedral?
Yes.
In layman's terms, what is wing dihedral?
It is.
I'm trying to look at this guy.
It would be the angle of the wing from its root on the fuselage. So like dihedral wings, instead of going flat out from the fuselage, they go up at an angle.
Very good. So here's the fuselage, and this particular aircraft is pointed at us. So the wing tips would have a tendency to go upward a little bit, like that, right? That is wing dihedral. What about aircraft like the B-52 or the Aviation Harrier? They don't have dihedral, do they?
No.
What would the downward angle represent? If you can remember. If you can't, don't worry about it. I got you.
That's... The word coming to my head is anhedral, but I don't think that's right.
Yeah, it's right. Have faith in yourself, man. Anhedral. Dihedral, wingtips going upward. Anhedral, wings going downward. Okay. Good. You thought you were wrong. Like, man, I don't think this is right. But I'm just going to take a stab. Okay. What do you think indicated altitude or indicated airspeed is? When we talk about that, what is indicated airspeed or indicated altitude?
That would be your altitude indicated based off of sea level.
No, indicated. And listen to the words indicated. Your indicated altitude or your indicated airspeed is the speed or the altitude you read directly off the instrument with your eyes. If you see, say, like 120 on your airspeed indicator, 120 is your indicated airspeed. All right. If you see 5,000 feet on your altimeter, that is your indicated altitude. That is directly what you're reading off the instrument.
Yeah.
All right. So indicated airspeed. What about don't know if I want to go into that area. So let me back up a little bit. What did I want to pick your brain about? What is a flight instrument inside the aircraft that's not powered by anything in the aircraft? Can you think of something? Doesn't use electricity, doesn't use pneumatics, doesn't use I said electricity, hydraulics, but it's a flight instrument.
The magnetic compass.
Yeah, the magnetic compass. And the magnetic compass is driven by the flux lines of the Earth.
Mm-hmm.
All right. Let's take the planet Earth for a moment. Wow, that's a pretty nice circle.
I was about to say, that's.
I'm getting better at this, man. I'm going to be an artiste. Okay. So, we're talking about our magnetic compass. And when we look at our North Pole and our South Pole,
Mm-hmm.
these are the lines that your lines of longitude go to.
Mm-hmm.
So they look something like this as you flew around. All right. But they all go to geographic, the geographic North or South Pole. Now, what your magnetic flux lines do, you have a magnetic north and you have a magnetic south pole. And this is what the flux lines of the Earth's magnetic field, this is where they kind of go.
Mm-hmm.
All right. So, you could never ever you flew north, it's taking you to the magnetic North Pole or the magnetic South Pole, not the geographic. Now, strangely, if you look at our charts that we use, sectional charts, WAC charts, TCA charts, you'll see lines of longitude. All right. And all those lines go to the North Pole, the longitude lines. All right. Now, we have something called magnetic variation. And we have something called isogonic lines. And you can find them on skyvector.com when you're doing your own research. But these isogonic lines give you the information to get to geographic north based on where you are on the planet. Mm-hmm. So it'll say 10 degrees east or 10 degrees west. And the memory aid is east is least, west is best. If it says 10 degrees east, you're going to subtract 10 degrees from your heading. And that will get you to the North Pole. If it's at 15 degrees west, you would increase your heading 15 degrees. And that will get you to the geographic North Pole.
Okay.
So we got a lot in. We got into 5 major components of aircraft. We talked about what each and every one of those components did. We talked about landing gear configuration. We talked about the use of flaps. We talked about what am I trying to say? We talked about the, gosh darn it, I'm drawing a blank.
Bernoulli's principle, we talked about that.
Yes, we did. We talked about Bernoulli's principle. We talked about the 4 strokes of reciprocating engines, and we talked about how they match what actually goes on inside a turbine engine. You still have intake, compression, power, and exhaust. They just do it differently. Mm-hmm. All right. So that will wrap up our first session of aviation and nautical information. Are there any quick questions? Was everything clear? Did something like not gel for you, whatever. I thought it was pretty self-explanatory. Well, not self-explanatory. I thought it was pretty clear. And if not, I'll clear up anything.
Yeah, everything.
Okay.
Yeah, everything was pretty clear.
Okay. The four forces of flight. We talked about the subcomponents of drag. We talked about ground effect. We talked about magnetic north and geographic north. We talked about the poles and isogonic lines. So we got quite a bit of information in there.
Yeah.
So I hope you were taking really, really good notes. And I think we're already scheduled for another day this week, aren't we?
Tomorrow at 5, if I recall.
Yeah. All right.
Yep.
So I'll see you tomorrow at 5.
Alrighty.
Okay. I'll see you later.
Yes, sir.
All right, folks. So that was just kind of like a little oral run through. I kind of send them through a chapter a little bit and say, okay, I want you to study this. And then we take time out and we kind of discuss it orally and stuff, because these are principles that you're going to have ready to go in your brain when you're taking the aviation selection test battery. Or even if you're taking a SIFT. Because, aeronautics, aerodynamics, all that good stuff it's kind of tough, and so you want to get it in and you want to know it like the back of your hand, because the questions could be presented in a way that might be a little bit confusing. But if you have basic aeronautical knowledge, it shouldn't be too much of a problem. So that's it. That's my last one for today. I thank you guys for watching. I thank you guys for the thumbs up, checking in. And I will see you guys soon. All right, we're... I'll get